Okay, so up until now we have talked about Riemann sums, making rectangles and finding areas under the curve, and antiderivatives. Well, now we're going to put the two things together. So the first thing you want to do is find the area under the curve from -4 to -2, from here to here. Well, up until now you would do a whole bunch of rectangles, right? And then like this, and then like this, and like that. Now that wouldn't be a very good approximation because you're missing all of this area and a little bit of this area down here. But you could do it, and each height is the value of the curve at that point. So this rectangle here is 1 times 8, so it's 8. This is 5, this is 2, and this is 0. But then if you added more rectangles, which they would be really hard to draw because you would be in between the actual nice values that I just used. But the more and more rectangles you draw, the closer and closer you would actually get to the real area. Well, what we're going to talk about now is what happens if you have infinitely many rectangles under the curve. Remember, the area under the curve is between the curve and the x-axis. So what would happen if you had 1,000,000 rectangles or more than 1,000,000 rectangles? Well, you would write it as the integral, and this is x squared minus 4 dx, because the height of each rectangle would be x squared minus 4, whatever the x value is put into the function to get the y value out. So that's what x squared minus 4 is. And then dx is the width of your infinitely many rectangles. So remember, they're really, really, really tiny, so we can't give them a number value. We just call them dx. So this is the height times the width, and that gives you the area of the rectangle. This s means sum, like add up all the rectangles, and it gives you the area under the curve. Now this area is above the x-axis, so therefore we would call that positive area. This area is below the x-axis. Now when you talk about this area right here from -2 to 2, you're underneath the curve. So your x values are still 1, but this time your y values are negative. So the area underneath the x-axis is actually a negative area. But you could do the same thing. You could draw a whole bunch of rectangles, figure out what you get, but if you draw them by hand, you're going to have some error involved because you can't draw infinitely many rectangles. So what we're going to do now is we're going to take this integral of x squared minus 4 dx, and we're going to find the actual area under the curve from -2 to 2. That's how you say this. The area under the curve x squared minus 4 from -2 to 2. This symbol is called an integral. These numbers are called your limits of integration. Your bottom limit of integration is -2, your top limit of integration is 2, and you're just going to go evaluate the function between those 2 points. But the really important thing to understand is that when the curve is under the x-axis, the area is negative because the y value is negative. So the height of each infinitely small rectangle is going to be negative. So this is a worksheet I gave you. If you don't have it or if you can't find it, please copy these problems down or print screen or do something. Make sure I just want to make sure you can see all the problems. This is the front and this is the back. But what it says is, your calculator believes the integral from 0 to pi of sine x dx equals 2. What are they talking about? Basically, what I need you to know is that this symbol means add up all the rectangles, and then the function is given, and then this dx thing is what messes everybody up. And I distinctly remember sitting in high school calculus saying, don't understand what we need with the dx thing. Well, let me try to explain it to you. If I were to do a left Riemann sum here, like that, and then like that, like that. If I just took each of those rectangles imagine a million rectangles between here and here. Is there any way to figure out what their width is? I mean, it's like pi over 1 million. Well, that's really, really, really small. In order to represent a really, really, really small value of x, we call it dx. It's just the change in x. The height of that rectangle, remember we drew rectangles, is the value of the function at that point. So it's the sine of x times the width of your rectangle gives you the area of one rectangle. And then this s means add up all the rectangles. Okay? So that's what this notation is. Now the worksheet tells you that the area from 0 to pi of sine x dx is 2. And then it wants you to use geometry to figure out all of these other areas. Okay? So I'd really like you to pause the video right now and look at this graph and see if you can answer the two questions at the top. And now I'm going to tell you the answers. From pi to 2 pi is exactly the same size as this one, but it's below the x-axis. So this answer would be -2. From 0 to 2 pi, these would cancel each other out, and it would equal 0. Now the next question asks you to shift the graph up 2 units. Now you might have to be able to do this without a calculator. I hope you would recognize that it's the exact same function as it was before. It's just shifted up 2 units. Ooh, geez, I didn't mean to do that. So if we're trying to find the area between this curve and the x-axis, well, we already know that the area of this part of it is 2. And how big is this rectangle? Well, it's pi times 2. So your answer for the whole thing would be 2 pi plus 2. 2 sine x just means it's twice as high. So the area is doubled. So this just equals 4. And then sine of x minus 2. Now on your paper, your numbers, these go by ones. On my paper, it goes by pi over 3, pi over 3, pi over 3. So if you think of this as being 3.14, my ones are like a little bit different than the ones on your paper. So this wants you to shift your graph to the right 2 units, not pi units, 2 full units. So you would move this way 2 units. Everything would shift that way 2 units. But your limits of integration are also shifting to the right 2 units. Remember, the original was from 0 to pi of sine of x dx. Well, if you add 2 to the bottom limit of integration, and you add 2 to the top limit of integration, and you move the whole graph to the right 2 units, nothing changes. Everything's the same exact size. So your answer is still 2. From negative pi to pi is simply 0 again, because these two cancel each other out. Sine of x over 2, well, you have to know what that graph looks like. And in order to know what that graph looks like, you have to know some of your trig functions, which hopefully you remember. Okay, I'm not sure if you can tell, but this is double what from 0 to pi is. It just gets extended to 0 to 2 pi. So the answer is actually 4. And remind me, we'll talk about that in class. Okay, so now on to the back. Oh no, more. Here's what the graph of cosine looks like from 0 to pi. As you can see, the amount above the x-axis is equal to the amount below, and therefore the integral is just 0. This area cancels out this area because we're only going to pi. Basically, from negative k to k for sine of x dx, if you think about the graph of sine of x dx, it's symmetric about the origin. So anything, if you go from negative to positive, it's going to cancel it out. So if you go from negative 2 pi to positive 2 pi, the amount above and below cancels out, and it's always going to equal 0. Okay, let's look at the back of this paper. Here's the graph of 7, y equals 7. I want to know the integral from 0 to 5. So if I draw a rectangle, just like this, and I move along the x-axis from 0 to 5, and I add up all the rectangles underneath, I'm going to get an area of 35. End of story. It's very basic. However, if I switch this around, and I move from 5 to 0, my changes in x's are all going to be negatives. So I'm going to be adding up a whole bunch of negative areas. Even though it's above the x-axis, the way I'm moving on the x-axis is in a negative direction. So that makes this area negative 35. This is important, the fact that when you switch the limits of integration, you get the negative of your original answer. That's going to be one of our rules of integration. Here's the next thing. Here's the line x plus 2. We want to know what the area under the curve is from -2 to +2. Now this is just a very basic triangle. Height is 4, width is 4, area is 8. Keep that in mind. We're going to come back to that. Same thing. This time you're going from 2 to 3. It's okay. What's the area under the curve? Well, it's a trapezoid, or in other words, it's a triangle and a square, and this is 1, and this area is 1, and so the whole area under the curve is 2. Here we have the graph of square root of 4 minus x squared, and from 2 to -2, I'm going backwards. So I'm going to find the area of this half a circle, but I'm going to make it negative because my dx, this part, is negative. These are positive, the 4 minus x squared square roots, but the dx is negative. So the area of a circle is pi r squared. Radius is 2. So the area of the whole circle is 4 pi. Half of it is 2 pi. But again, because I'm going from 2 to -2, the answer is -2 pi. Finally, when we look at the graph of negative square root of 4 minus x squared, the entire graph is below the x-axis. So everything in this area is negative. However, I'm integrating from 0 to -2. So my dx is negative. So I have a negative dx and a negative y value. That's going to give me a positive area, and it's a quarter of the same circle. So we said the area of the whole circle is 4 pi, so a quarter of it is pi. And the y value is negative, and the x value is negative, so the area is simply positive pi. Fundamental Theorem of Calculus Part 2. It's in your book on page 364 if you want to see it not snipped and pasted into this little thing. But what it is saying is, if you take the antiderivative of your function and you plug in the top limit of integration and you subtract the bottom limit of integration, you will get the area under the curve. Let's go back and look at what we've been doing and see how that worked. Take a look at this one, for example. Why is it not taking up the whole screen? There we go. If I asked you to find the antiderivative of -2x plus 3, you would tell me -x squared plus 3x, I hope, because that is the antiderivative. And then you have a plus c usually, but we're not going to write the plus c because we're going to plug these numbers in. So I'm going to plug in the top limit of integration, and that gives me 0, minus, plug in the bottom limit of integration, and that's -4 plus 6, which is 2, and then I have, right, -4 plus 6 is 2, so I have 0 minus 2, so the answer is -2. Apparently when I wrote this down, I forgot that all of this area was under the x-axis, so the answer should have been -2. Check this one. The antiderivative of x plus 2 is 1/2 x squared plus 2x. And if we evaluate it from -2 to 2, well, when I plug 2 in, I get 2 plus 4, which is 6, minus, plug in -2, you get 2 minus 4, which is -2. 6 minus -2 is 8. Isn't that amazing how that works? I love it. Love it, love it, love it. Okay, back to these guys. So remember we said we were going to come back to this one? Well, if I take the antiderivative of sine, I get negative cosine. But there's an x over 2 here, which means I needed to multiply by a 2 at the beginning to make that 1/2 go away. And if I evaluate from 0 to 2 pi, 2 pi over 2 is pi. Cosine of pi is -1. You should know that by now. -2 times -1 is 2. Minus, plug in 0. Cosine of 0 is 1. -2 times 1 is -2. 2 minus -2 is 4, which is what we said the answer was. Go back and try this for all the ones we've done, and hopefully it's like a wow moment because it is pretty cool.